Hey, it's Joel, and we get to show you a lot of hobby level and consumer level 3D printing here on the show. Now, we get to show you a new world of 3D printing, Industrial Additive Manufacturing. Let's go see how Siemens is managing the product life cycle for Industrial Additive Manufacturing, right here on 3D Printing Nerd. Hey, Nicholas.
Hi, Joel.
What is your title here at Siemens?
I am a thought leadership manager for industrialization of additive manufacturing.
Oh, and that seems appropriate because what we have behind us looks pretty additive manufacturing focused.
It is focusing on the industrialization of additive manufacturing. And we are showing our entire digital enterprise portfolio, which works for machine builders as well as for end users for additive manufacturing.
Sounds great. And this is what manages the entire product lifecycle.
Totally, from product design through all the different phases to services, entire product lifecycle. And again, for machine builders and product developers alike. Maybe we should just look right into it.
Sounds like a plan.
Yeah, let's do it. Come, follow me. So Joel, obviously the first step is product design. And
Makes sense.
With Siemens NX, we're showing on this station how the software suite really enables our customers to do CAD, CAM, and also CAE modeling in our environment.
CAD, CAD-based stuff. What is CAM?
CAM is computer-aided manufacturing. So programming your manufacturing processes in the same software suite based on the same data set. And we have SIMCENTER as our data backbone that enables the data management for the production distributed across the world. And it's being used by many customers around the world as well.
So it's not just a single user. This manages the team of people that are using it.
Team of people, exactly, to work together on the same data set, so to speak. And it gets very important, specifically in additive manufacturing, to also utilize simulation features. And this is what we have on board as well in our very rich simulation package. And let's look into what this allows you to do for additive manufacturing.
Perfect.
We'll hand you over to Simon to explain a little bit more in detail what that means in a specific way.
Hey, Simon.
Hey, good to see you.
Good to see you. Design optimization with SIMCENTER. What does that mean?
Well, actually, you have to understand, in this particular case, we talk about fluid dynamics simulation, right?
Oh, I understand that.
Okay, you get that? So actually, here we look at a particular case that came from HP to us. HP do printers, as you know. We're now inside the printer, and we're in the assembly that carries the printer head, which is, in a second you will see, there's down there, you will see the two printer heads for the color and for the black. And actually, those two guys, they have to be cooled, right? So because if they get too hot, you cannot print fast enough.
And this is the airflow visualization going to the
Exactly, you got it, right? And we took the blue color just fitting your...
I appreciate that.
Yeah, sure.
I'm a big fan.
So, talk about fans. This is the fan down here, right? Mm-hmm. And it drives the flow. And as you can imagine, that thing spins at 10,000 RPM, which is quite a lot.
It's quite fast.
If you consider yourself, right, you want to get forward, and I don't know, you start swirling around, of course that's not efficient, right?
Right, spinning doesn't mean forward.
Yes, it's like you come out of the pub and had too many beers and then you want to move forward. It's not ideal to spin in circles.
That's right, it is not ideal. So how is SIMCENTER going to solve this?
So as you could see, we were able to solve this flow for the, let's say, the original design, right? And if we look at the details here, it is super turbulent, and turbulence means actually a waste of energy, right? Mm-hmm. If you generate too much turbulence, then you just waste all the energy that you actually want to use in order to really bring air mass forward. You could see in a little more technical detail here that the velocity is really high in terms of the swirling motion. So,
meaning that there's a lot, that red means there's a lot of energy being spent in swirling around.
Exactly. So what we did is we used the same CFD fluid dynamics simulation technology, but on top of it, we added something called topology optimization, right?
I've heard of topology optimization, and I've seen some people talk about it, but in reference to fluid dynamics, I haven't seen this before.
Okay. So what topology optimization means is you have an algorithm, some intelligence that starts to understand which part of the geometry is not beneficial to reach your goal, right? Imagine yourself, you have to run a marathon, right?
Okay.
And you have to be as fast as possible. That's your goal, right? This algorithm will tell you which is not beneficial. It's like if your knee hurts after the marathon, you will get an idea. I have to train my knee. Next time you run the marathon, maybe it's your heel that hurts, right?
Okay.
So you train your heel and you get better and better because you understand which part hurts the most. You remove that from the issue, right? That's what the algorithm does.
Oh, so I need an algorithm to help me run faster in a marathon without hurting myself in the end.
Yes, but you have to run it over and over and over. I'm
That's
sorry.
the problem.
So we do this in a digital world here with a slightly different application, but the idea is still the same. So now you see the baseline configuration and you see how the algorithm eats up all the available space to the fluid.
Oh, so the simulation, a fluid dynamics simulation, is actually sending the airflow through this space,
Yes.
and then where the airflow isn't touching, the algorithm is able to remove those bits of that available space because it knows the airflow is not going to hit it.
It's not about hitting it, it understands, okay, if I removed the available space here, then it would be more efficient for the airflow to go through, right? That's the idea.
I see what you're saying.
Okay. And you end up with something that looks pretty odd in first place.
Yeah, that is odd looking, that is for sure.
So what's next is, we give this to our colleagues that smooth a little bit the surface, because you always have in these algorithms, you have some artifacts that you need to remove, but after that, you end up with something that is more smooth, but still looks odd, right?
Right. I'm looking at this, and it's fascinating to see that this was a generated shape, but it's smooth. It's still odd,
Yes.
but it's smooth, and according to that, it is far better.
If you look at that now, the idea is to guide the flow in a very nice, organic way from this swirling motion. You force it to go into this tangential motion, so to better go in a streamlined way. But this means we were able to improve the mass flow by 22%.
You've improved cooling on this printer
Exactly.
22%.
Yes. And the good news here is, really, all this, the whole simulation we've just seen, this took like less than 8 hours, right? With me going home, having coffee, and the simulation was going on autonomously, right? So what does that mean? Next step, of course, is this real? So we talk about a digital thing here. So they brought it to life. That's the point number one. They were able to print that thing, and you cannot manufacture something like that without...
That is not an easily manufactured shape
Yes.
at all.
That's the really cool news for somebody like me that spend a lot of time on fluids. When you came up with these kind of solution in the past, which were flow optimized maybe, people would say, I'm sorry, I cannot manufacture it here, right?
This is incredible because, I mean, you have the simulation that allows you to refine the shape to something that's going to be more efficient, but then that's going to generate a shape that isn't manufacturable. But thanks to additive manufacturing now,
Exactly.
this simulation creates a shape that can now be produced.
Yes.
I mean, it's got a tongue.
Yes, it has, yeah.
Just needs two eyeballs right there, and then it'd be like a pet.
I can tell you I've seen a special edition of that one. And look at that. This is what it actually looked like before we did the optimization. Check this out.
Okay, so this looks like a standard vent, essentially, a standard part that would be injection molded maybe?
At least that one was printed as well. That was the first step for them to take it to the next level. Beforehand, they had all these parts they had to assemble together. Then they started to print it, but still they were not happy. They wanted to increase the performance, right? So we took it to the next level by that means.
This is fantastic.
It's pretty
wow. Oh, Simon, thank you so much for
You're
this.
welcome.
I promise I won't
And-
steal this, but that's really cool.
And you can imagine the potential is huge, right? This was just one example. We were inside a printer, but computational fluid dynamics is out there everywhere, right? We serve all the industries. We serve the automotive industry, the aerospace industry, oil and gas, energy production. We do even medical devices. Everywhere where you can imagine something flows or is a fluid, there is potential for this technology, right?
Absolutely. What's great is the potential is there, and you have the ability to manufacture the parts now. I'm going to give you one more of those. Thank you again.
You're welcome. It was a pleasure.
Hey, Nicholas.
Hey, Joel.
What's next?
Well, now I think it's time to look into a really cool parts that are made in additive manufacturing. And
These are it, right?
These are it. This is where we talk about industrialized serial production in powder bed fusion.
Serialized meaning?
Meaning hundreds or thousands of parts, similar or same parts in a big production capacity.
Okay.
Having the process parameters already set and predefined and found and fine-tuned, but still this is where our entire solution really comes together from product design over simulation to optimize the whole build job on a digital twin and then print on a machine, in this case on an EOS M400 shared modules machine, print these parts in a reliable way.
So by digital twin, you mean the digital representation of this model?
Exactly. We're thinking about the digital twin of the product, the production, and the performance. And the digital twin of the product is where you do your design and your simulation of the single component. Digital twin of the production would then already be the preparation of the build job and the simulation of the build job. You want to know that what you put onto the machine and what print job you start is actually turning out well. We call that first-time right printing.
I see. Okay. Well, by digital twin, you think of a one-to-one relationship being a twin, but it's not just the part itself. It's the process around the part. It's the simulation with the part, and that travels with it.
Exactly. And what's really cool here, one specific feature to mention is if you're talking about serial production, our customers want to handle serial numbers as well, or unique identifier codes. This is a new feature we have available in our NX software, where you can dedicate a specific serial number to a given number of parts. And in this case, to 16 of these swirlers that go into a gas turbine, the final component that's sold in a gas turbine. And you can put individual serial numbers on each of these parts based on a database and make it very easy to take the data from your ERP system and put it and identify it to a specific part.
So NX would then have access to this.
Yes.
You say there's 16 parts here, and pull and get the next 16 numbers.
Exactly.
And give them to each of the parts.
And give them to each of the parts and print it then automatically on the machine.
That's cool.
Yeah.
These look really neat.
I know, yeah. Still a long printing process, but this is amazing. And this is real industrialized serial production for powder bed fusion metal parts.
Well, and it makes sense that you're having to do many of these, and so you have to take advantage of all of the build space, and you can see the clearance between parts is very minimal.
It's completely optimized to get the best output and the best yield and optimize the build space, in this case 400 by 400 millimeters in XY direction, and put as many products in and really have the best utilization of the machine. Speaking of the machine, one more thing, our Digital Enterprise Portfolio also contains automation equipment. So drives, controls, motors, and so on. This is something that we provide to OEMs as well.
Oh, that sounds great.
Yes.
So it looks like we have a bed of parts here. This one is just a one-off, is that right?
It's a one-off. Not a serial production part. It's a motor gearing bracket, but we can show some amazing things on this part. This has been topology optimized, so we're optimizing for low weight, but still the same rigidness that you need in a part to be used, in this case, in a racing car. But it's pretty amazing because on this part we also show our customers the build process simulation, because our customers want to make sure, again, that what they send to the machine is printed correctly. And there's a lot of thermal influence in the metal printing process, you're aware of it. So we have to make sure that we can account for this and correct the geometry of the part beforehand if needed.
And that correction happens digitally.
It happens digitally. It happens in the software SIMCENTER 3D AM. We can simulate the interaction of the laser in the machine, or in this case of many lasers, 4 lasers, in the machine with the material in the machine, with the powder, and see the thermal influence and the results, the deformation. And then we can go ahead and in the software correct the deformation and create a predeformed geometry that we can then print on the machine, and is turning out correctly.
And with that simulation then, you know that this is going to be the best version of this available using the machine you used.
Exactly, and you want to minimize the risk of failures during the printing process, because that can cost a lot of time and money. It can be very expensive, and our customers want to make sure first time right printing again. And this is possible with our Digital Enterprise Portfolio.
It seems to make sense though, right? You would want to simulate or approximate as accurately as possible everything before setting one of these go, because this takes a long time to make, and it's very expensive if a failure happens.
Exactly.
And so this ensures that failures aren't going to happen. You said the first time right print?
First time right printing.
Okay.
Process robustness is really what our customers want to have, and with the right preparation of the digital data, this is something that really supports this strongly.
So cool.
Yeah, it's pretty nice.
It is cool. I mean, you can tell the shape is not something that you would normally think of, so it has been optimized.
Yeah, software becomes the designer. Software designs this part. This is not something the human does. The human says, okay, there's some flanges that have to be in a certain position, have a certain geometry, but other than that, you just give it the load situation, the forces, and then the software takes over.
That's so cool, because it produces amazing looking parts, but good parts, less material, less money, same strength.
So this is where really the software, the digital twin, again plays its strength. So we've looked into our product SIMCENTER 3D AM to do the process simulation as well, but we're working on a research topic that is really exciting, and I would like to hand over to Omar to explain this to you.
I like this. All right, thank you, man.
Yeah.
Hey, Omar.
Hey, Joe.
Nice to meet you.
Nice to meet you. Welcome.
Thank you. What are we doing here?
Well, what I've tried to explain to you is how we take additive manufacturing from prototyping to serial production and make great components out of metal additive manufacturing.
And so what's the current problem with doing that?
Well, to be honest with you, there are a few challenges, tough engineering challenges. And the one we are focusing on at Siemens is how can we make additive consistent, meaning we produce the same component multiple times with exactly same quality.
Oh, so when you're doing this, you have the same essentially model or the same G code or whatever,
Yes.
and that's kind of going and creating the same part, but those parts aren't all the same?
Absolutely. It's a
Oh.
tricky technology. Let me explain to you. Sometimes we have a strange interaction between the laser and the material that creates localized defects, and those are really difficult to detect, and what we want to do is to detect and predict them. So what we essentially want to do is to simulate all the scan path. The problem is, if you use finite element, which is traditional finite element simulation, it might take a long time. Do you have any idea how long it will take to simulate all the tracks on this component?
Okay, so this component, laser moving about a powder bed, and we're having to simulate the entire model over
Correct.
time. I'm going to take a guess at like a week.
Oh, wow, you're so far away from the... I'm sorry about that. It is concretely around 2,000 years of
What?
simulation. Yes, it's crazy, isn't it?
That's a long time.
Yeah, unfortunately, physics-based simulation are complicated, require huge computational effort. But we at Siemens had an idea, a great idea. And I want to share with you this, and I'm really not joking. This is the first time we're bringing machine learning to additive manufacturing.
Machine learning.
Yes.
And this is going to help with the simulation.
Absolutely. We have developed with our corporate technology an approach where we are training a machine learning algorithm on physics-based simulation. This is a tricky approach.
Yeah.
The machine learning is learning essentially and becoming better with time until a point that could do the same simulation but faster.
How much faster are we talking?
So we're talking about this component, as I said, 2,000 years on my laptop. And now we're doing this in 30 minutes essentially.
30 minutes.
30 minutes.
You've had a reduction in time for building the simulation from 2,000 years to 30 minutes.
Yes.
That's incredible.
Well, really, what is incredible is not this. What is incredible is now we're helping our customers, our businesses, to predict these defects and to correct them and to make better components and to enable additive manufacturing at scale. Industrial additive manufacturing, as you like to call it.
So being able to accurately predict via simulation means you're going to get consistent parts.
Absolutely. And the detail, as we say, is in the devil is in the detail.
The
right?
devil is in the
devil
details.
is in the detail. And this is a good example I wanted to share with you and offer you, by the way, from Siemens as a gift, so you can share this information with a lot of people.
Fantastic.
So these are two industrial scale components. Maybe you will detect the problem, but I have a picture here with zoom for you.
So the edges over here look a little smoother.
Absolutely.
But I mean, this is just human eye at,
I have a magnified
a bit
picture
away.
for you.
Let's see it.
Yeah, and look, when we zoom on it, you don't want to have this in industrial additive manufacturing. You rather want to have something smooth, consistent, and of a high quality.
Oh, so because this is essentially a randomized pattern.
It is not randomized. It is the same pattern, but less optimized.
Oh, okay.
So now we used our simulation to predict where the problem is, and we went and we corrected it. Up front, best process planning you can do for additive manufacturing. And with this technology, really, we are helping a lot of people bring consistency, quality, and safety.
Oh, I see what you're saying. So a part like this, while it still may visually look okay, this would never be qualified.
It will not be
You couldn't
qualified.
use this in production.
No, you can't. Because without getting too much into the detail, the microstructure of the material here will be different than here, and quality therefore.
And this part, because it's been corrected and it's consistent, could now be used in production.
Absolutely. And we are doing this with our internal factories. We are testing this solution, and we're hoping next year to industrialize additive manufacturing, hopefully.
This is really cool,
Yeah.
Omar. This is really cool. Omar, looking at this, this one, it looks, I mean, it doesn't look bad, right? And this one doesn't look bad, but once you put them together and you look, it's as clear.
Absolutely.
It's as clear as night and day. This is amazing, and it's crazy how much better, even just under a minimal amount of magnification, that I'm able to tell that a part is better. And this is me, an untrained eye.
No, Joe, I think you have got it all. This is really in the details, and I'm very happy that you have seen it. And yeah, so this is how we combine software, machine learning, mathematics, physics together to solve tough challenges for additive manufacturing.
So some people run physics simulations to power video games. You're running it to make better parts.
Well, it's our kind of gaming also.
That's true.
That's what we do at work. We have fun.
Thank you very much.
Joe, thank you for coming, and I hope I can show you some advanced technology next year.
Sounds
Same
like a plan.
place.
Well, that was cool. What's next?
Well, Joel, let's look into something that the Digital Enterprise Portfolio offers for machine builders. So the companies that making 3D printers and 3D printing machines, additive manufacturing machines. In this portfolio, we have the same elements. You know, they want to design their machine. The product then is the machine and not the printed product for the machine builders, obviously. And that's what we have available here, yeah. And they can design the machine in Siemens NX as well, same CAD software program. But we also have, with the Mechatronics Concept Designer, for instance, a whole engine to validate and simulate the behavior of the machine and do the programming with for making sure that this machine runs accordingly.
And this is this is simulating a physical machine that someone might be looking to make.
Yes, exactly. And also simulating the code that you program for the machine to do certain things. When you open a door, you want to make sure the machine turns off, the light goes on, and so on. And this is what we can all validate here on this tool, on this digital twin of the product, on the digital twin of the machine, and really make sure that this machine can be virtually commissioned before it actually physically exists.
Oh, so someone who's manufacturing a 3D printer then could, if they have a specific job that they're building it for, then they virtually commission this to make sure that what they want to build will work.
Yes.
And then they can build it.
And moreover, they can also sell the digital twin of the machine or offer it to customers that they sold the machine to, but maybe the machine is still in production and takes months or weeks to deliver. And the customer can train on the machine, on the digital representation, the digital twin of the machine, can train the operation and how the machine behaves based on this tool.
That's really cool, because that's going to cut down on downtime, then, obviously.
Exactly, getting everybody up to speed before the machine is physically available.
And then once it's available, they go.
They just get going, and print as many parts as possible.
That's pretty awesome.
Yeah. It's a whole holistic approach for machine builders as well as for end users. Really incorporating all the digital tools you need to be set to go.
Well, it makes sense. You're already simulating the models, the print bed, the job. Now you're simulating through the digital twin the machine itself that's doing
the machine behavior. Exactly.
That's cool.
Yeah. So let's look into something else that I want to show you. It's really cool. So you want to follow me?
I will.
Let's continue.
So, Nicholas, we have a digital twin of the model. We have a digital twin of the machine.
As well, yeah.
Is this a digital twin of the factory?
It kind of is, yeah. It kind of is.
What is this?
It's pretty cool. This allows our customers to really take it to the next level and scale the production. Whether they already have some printing facility and printing capacity, or they're starting from scratch, they probably want to make sure if their investment is sane. You know, they want to make sure that what they buy, what they plan to do, is sane and makes sense. And this is what they can do with this kind of software. This is based on Technomatic's plant simulation, also a Siemens software. Allows you to completely simulate factory environments and everything that comes with it. Different layouts, different production scenarios, and so on. And we have printed small models.
I was going to say, these are 3D printed 3D printers.
Yeah. Well, they represent, 3D printed, and they represent 3D printers, different kinds of 3D printers on additive manufacturing machines. We have EOS machines, we have HP printing machines, DMG Mori, but also post-processing. Post-processing is an often neglected element of the whole life cycle again. And there are a lot of machines also equipped with Siemens automation that are really good for post-processing as well. And all of these machines you can print and are available here, and you can play around with them physically to make sure that you understand what you're planning to do in your facility later on.
Oh, someone who's building an AM facility then is like, I need a couple machines, I need a couple post-processing stations.
Yes.
Where do I put them? How is it going to look?
And how many do I need? Sometimes they don't know the right setup. They don't know if they need one printer and how many AGVs or operators and how many post-processing machines or ovens or stuff like that, sewing machines, all part of the industrialized additive manufacturing world. And they want to make sure that some software can help them simulate this, the setup, the plant setup, and know the outcome before they make an investment decision. And we can actually play around with this. So the camera picks up these kind of codes or coders, and then you can move around. This is you in this case, or me,
This is me.
or us standing in
May
the.
I?
Yeah, go around, knock yourself
Okay,
out.
oh, look at that. Oh, wait. Did I see? Is
Yeah.
there a window? Is that a sunny day outside?
Must be a sunny day if they have so many cool 3D printers and additive manufacturing machines. Let me block your vision. So you see,
Oh, you just...
yeah, I just put a machine in front of you. So yeah, this is the real connection between the virtual and the real world.
Wow. So I could, if I had an AM facility that I was planning,
Yeah.
I could, it's almost like a video game here.
It's like Tetris a little bit, you
A
know?
little
You can-
bit.
And then you can get a feeling of the dimensions and so on. These are all in the same scale, scaled down, obviously.
Obviously.
But all in the same scale, and you can get a really good feeling of what are the available spaces. You can still move around. You have logistics areas and so on, and yeah, really have it immediately represented in the in the virtual world.
But look at that, it picked it up.
Yeah.
Wow.
It did.
Okay.
Yeah. It's difficult to confuse the system, but I don't think it's the right setup. We should improve on that.
I should probably
We're still
not be
practicing.
I should probably not be the one designing an AM facility at this point.
Yeah. But here really the software helps you to find the right results and also get everybody on board. We have different stakeholders that want to participate, but they don't just want to look at a screen. They don't get a feeling of dimension. They want to also be able to touch real parts and yeah, just imagine better what this is going to look like in real life.
But it seems like if I'm going to spend millions and millions of dollars, I should know every aspect of it as much as possible. And,
exactly.
and being able to simulate this layout of an AM facility, I'm going to know exactly what I get in the end.
Yes, exactly. And you can get support from our IoT service consulting experts who can help you really scale your production facility, and they are skilled in using those tools and supporting you and using this. And yeah, again, the software and the digital enterprise portfolio really helps you with that scalability. Well, there's something else I want to show you, and we have a lot to cover, so maybe want to move on?
Let's do it.
Let's go. Remember this?
Hey, I remember that.
Yeah.
I was in Worcester.
Exactly.
And it's the steering box for the Ruston.
For the Ruston car, exactly. It's from our experts at Material Solutions, and yeah, they help customers repair old-timers as well as make amazing new parts.
That's a cool facility. I had a lot of fun out there.
It's great. It's great. It's also real industrialized additive manufacturing.
Yeah.
Yeah. We are here because we're showing our global additive manufacturing network.
What is that?
It's a platform that connects the entire ecosystem in additive manufacturing. So print service providers, designers, consultants, experts, OEMs, and so on, software vendors, all on the same platform. Brings together the whole ecosystem to expedite really the interaction between all these players.
This sounds like an industrial 3D hubs.
Yeah. It's a good way to say it. Yeah, it's going in the same similar direction, but it's also often being used already from customers in-house. So they're not even providing the print services or the services externally. They're using the whole system inside in-house because they have maybe a design department that's completely elsewhere than the printing facility, and they want to send their prints and interact on different designs and changes and so on very fast. And they can do it over this platform, but keep the IP completely in-house.
I see what you're saying. So it's a network, but it's a solution that can be used in-house, essentially.
Exactly.
But in-house meaning a company that has different departments.
Yeah, but it can also be used externally, and Material Solutions is one service provider being available and offering services over the AM network as well. Mobility as well from Siemens. So there are a lot of external service providers already working with it. But it can be used in-house as a standalone system so you don't exit and give any IP away.
So then if I had Siemens NX and I
Yeah.
designed something
Yes.
and I simulated it and everything was good and I needed to find someone to provide a print of it,
Yeah.
I could use this.
Yes, exactly. That can help you a lot finding the right people for the right technology to find the right printing service provider. To
Oh,
do
that's
that.
right, because there's all the different types of printing.
Yeah, there's a lot of different AM
okay.
technology modalities.
Perfect.
Yeah. Well, there's one really cool other highlight I would like to show you.
Oh, where is it?
Shall we look at it?
Yeah.
Go in the direction. Let's follow me.
Nicholas, what is this?
This is amazing. This is a multi-axis robotic printing solution. It's a great example for collaboration. The robot extrusion system comes from Seed, company Seed. The mechanics of the robotics comes from Comau, and Siemens is providing the controls, the CNC control, the motors, the drives, and so on.
So it's able to 3D print because of the Siemens
Exactly,
control.
exactly. All the axis and motions of the axis is controlled with our numeric CNC controller. It's pretty cool, right?
That's really cool, Nicholas.
I
That is
know.
really cool.
Yeah, I'm excited to have it on the booth. But don't worry, there might be more of this later. to
Really?
come. Yeah.
Okay.
Yeah.
Okay. Well, hey, a big thanks for bringing me on this journey, my friend.
It was my pleasure.
That was a lot of fun.
Yeah.
Thanks to you for coming out and watching this. If you made it this far, you're awesome. Don't forget to hug each other more. I love you all. As always, Schlagai.
High five.